Have you ever looked at your phone or been sitting there watching TV or played on the computer and ever thought, how do you possibly go from this to that? To be honest, the process going from sand to the electronic devices we have today is extremely complicated, but we're going to go through it step by step and simplify things so you can understand exactly how this process takes place. So the first step starts obviously here with sand, or more specifically, silicon dioxide or quartz. Now here at the Bruno Sand Dunes, this is only about 50% pure, which isn't good enough for our purposes. We need something of much higher quality. Once you find quartz of high enough purity, then you want to melt it down, much like I'm melting down this sugar to create candy. As I'm doing this, I actually want to wipe down the sides to make sure that any sugar crystals that are forming on the sides are melted down and don't act as seeds in the rest of my sugar, because I don't want those seeds to spread and cause all of my sugar to recrystallize, because that's gross. However, when I'm creating an ingot or a cylinder of semiconductor or silicon dioxide, that's exactly what I want. So what we'll do is we'll take a seed of silicon dioxide that has a good crystal structure and dip it into molten silicon dioxide and then slowly pull it out. As you're doing so, it creates this perfect silicon dioxide crystal structure, which is exactly what we want. Now, as we've been getting better and better at it, we've been making bigger and bigger ingots, and the bigger the better, because you get more usable space out of it. And then once we have these perfect ingots, we slice them into really thin wafers. Now this wafer of silicon is what we call a semiconductor. In this state, it can conduct electricity, but not very well. Semiconductor. Get it? To make this thing useful, you need to be able to control that conductivity. Now, we've gone into detail about the process in other tutorials, but for this, I'm just going to say that if you add either boron or phosphorus to this silicon, a process called doping, you can change the conductivity by creating N-type or P-type semiconductor materials. But you don't need to know how they're different, but the important thing is if you put these N and P-type materials together, you can create structures that, with properly applied voltage, control the flow of electricity. You then add other materials like metals for connections. Now that's easy to say, but doing it is another matter. Often the wafer isn't actually pure silicon dioxide, but has already had impurities added to it intentionally when creating the ingot. To create the patterns of different materials they want, it can take dozens of different processes. One such process is done by putting a layer of chemical on the silicon called photoresist. You shine a light on the silicon through a mask to create a pattern of light on the resist that you want, and then that exposed resist is hardened. You then use an acid to etch away the unexposed photoresist. Then, using either diffusion or ion implantation, you shoot the boron or phosphorus, which creates a well in the exposed silicon substrate that is now either an N or P-type semiconductor. So now we have literally billions of N-type pieces of semiconductor jammed up with billions of P-type pieces of semiconductor, but what is that doing for us? Now, this is where we get that transition from the material science side of things over to the electrical engineering side of things. Now, there's a bit of overlap between the two engineering types, but mostly I just think that's amazing in that it shows exactly how many people and how diverse of backgrounds are needed to make this entire process work. With electrical engineering, we use the ability to control the conductivity of this semiconductor material to create transistors, devices that can act as switches or as amplifiers. We'll only consider them as switches for this, and you can control them by giving them a voltage to either open or close the switch. Their symbol looks like this, where the voltage at the gate controls whether electricity can flow from the source to the drain, but in real life, they look more like this. The interesting thing is that the famous Moore's Law is about these transistors, stating that the amount of transistors in a microprocessor doubles every 24 months. So as these switches get smaller and smaller, and they shove more of them into microprocessors, it makes them both switch on and off faster, and you can do more things for the same amount of space and power. As of right now, there are billions of transistors in modern CPUs, and in the unlikely case where Moore's Law continues, in 20 years there will be trillions of them. So now the next step is we move into digital logic, where we use these switches to create digital devices, basically devices that think in ones or zeros. Now, in reality, a 1 is simply a high voltage and 0 is simply a low voltage, but once you know that, you can kind of ignore the voltages and just think in the ones and the zeros. So with that, let's use a NOT gate as an example. Sometimes you want to put in a high voltage and get out a low voltage, or put in a low voltage and you want a high voltage out. With this structure, you have the top device, a P MOSFET, and the bottom device, an N MOSFET. When the input is high, the PMOS is turned off and the NMOS is turned on, so the output is connected to ground, which is a low voltage. When the input is low, the NMOS is turned off, the PMOS is turned on, so the output is connected to VDD, which is a high voltage. So you invert the signal. This creates the NOT gate. This same process is how you use transistors to create all of the digital logic gates like AND, OR, XOR, and their inverses, NAND, NOR, and XNOR. And at this point, you can just start thinking of things as 1 or 0 and doing binary math. You can create things like adders, multipliers, and other subcircuits that can be connected together to create something greater. We'll actually go over an adder in a moment. We've done a tutorial on binary, and I highly recommend you go check that out to get more detail. But in essence, the way we count in decimal is that we count from 0 to 9 and then move over a spot and add another 0 to 9 digit to make the number bigger. The first spot has values from 0 to 9, the second 10 to 90, the third 100 to 900, or in other words, the first spot is whatever number you put in there multiplied by 10 to the 0. Then the second spot is whatever number you put in there multiplied by 10 to the 1, 10 to the 2, 10 to the 3, and so on. With binary, the multiplier is 2 instead of 10. So instead of 0 to 9, you have 0 to 1. And instead of multiplying it by 10 to the 0, 10 to the 1, and so on, you're multiplying by 2 to the 0, 2 to the 1, and so on. Again, we have an entire tutorial on this stuff, so if you want to learn more about it, go check it out. Now we need to understand that binary to get something out of the digital logic gates that we're putting together. Now, 1 plus 1 may seem like one of the easiest things in the world to somebody in kindergarten, but in digital logic, it's both incredibly complicated, but at the same time, doing it is one of the simplest structures that you can make. So we're actually going to go over a full adder, which shows how we can take those ones and zeros and turn it into something that we almost would understand as normal human beings. Here we have 3 types of gates, an XOR, an AND, and an OR gate. Our inputs are A, B, and Cin, where Cin is the output from another full adder, as these are used in groups so you can work with realistic numbers. You can see that the input goes into an XOR, which only gives a high output if one and only one input is high. So if you are adding 0 plus 0, the output from that first XOR is 0. The 0 output from the first XOR goes into the second XOR, and if we don't have any carryover from another full adder, the 2 0 inputs to the second XOR gives us a 0 on the output to the line S. Congratulations, we just found out that 0 plus 0 equals 0. Now let's do that again with 1 plus 0. Now if A is 1 and B is 0, then the output of that first XOR is going to be 1. Again, assuming that Cn is 0 with a 1 and a 0 going into that second XOR, you get a 1 output on S. So now we know that 1 plus 0 is 1. But if A and B are both 1, then the output of that first XOR is 0, which, again, assuming Cn is 0, then the output to S is 0. Wait, 1 plus 1 equals 0? The problem is that with binary, you don't have the number 2. So this is where those AND and OR gates come in. The output from that first XOR goes into that first AND gate, and if you have both a high output from the XOR and Xin, then the output of that AND gate will be 0, so we're still at 0. But A and B both go into the other AND gate, and if both A and B are 1, then the output of that AND gate will be 1, which will go into the OR gate. And if either of the inputs into the OR gate are 1, then the output, Cout, is 1. So while the output S is 0, Cout is 1, which, depending on where it goes, can be considered the value 2. Now, instead of going through each one of these manually, there are truth tables that show, given the value of the inputs, what the output values will be. With these truth tables and understanding how everything works, you can put a bunch of these full adders together to make something that can add much larger numbers than just 1 plus 1. Now, once you've created these modules, the arithmetic modules, memory modules, address decoders and encoders, clocks, and more, you can now put them together into a computer. Putting these all together in a way that actually makes sense is called computer architecture, much as you take housing materials and put them together to actually make a house. This is where you create the overarching structure. The way you put the structures together makes a huge difference. You look at all those chips, AMD, Intel, ARM, they're putting together the logic gates in a way that they think is the most effective or efficient to add, multiply, or remember things. It's not just the size of their transistors. At this level, while creating the computer architecture, the digital logic is complicated enough that data starts to need to be clocked, flowing through the process in such a way that it takes several cycles for the information to go through the entire thing. And this is where you start crossing the boundary between electrical engineering, which is my background, and computer science, which is my brother Sam's, who's been kind enough to help me with this last portion. Once the architecture is put together, you've approached the lowest level programming code, or machine code. This is where software meets hardware. The closest you can get to this level of programming is probably found in our PIC10F200 assembly language tutorials. At this point, you can load values into the memory, which are basically switches that store information, and that will control the way information flows through the computer architecture. On top of this machine code, you can build up the layers of software. From machine code, you can go up to assembly, or go up to a higher level language like C, or even higher with C++, Java, Python, and languages like that. And you're now at the point most people are familiar with. You create an operating system. Now, an operating system is basically a layer between the hardware and software that standardizes the communication between programs and the peripherals. Imagine if every time somebody wanted to create a program, they had to figure out which CPU their target audience was using and how to make it so that the mouse their audience was using could interact with the CPU. It would be a mess. So the operating system takes care of that and makes it so that programmers don't really care about anything other than the interface point. It also allows a program to pretend like it's the only program and protects each program from one another. Now, the interesting thing about the differences between the operating systems is with Mac OS versus Windows, it's all about the hardware. Mac OS, they decided, is only going to work with a very select type of hardware that they provided, and so they could make things more streamlined and basically make things more secure because they had more control over it. Whereas with Windows, they decided they wanted their operating system to work with a lot more hardware, which makes it harder and a little bit more bloaty, but it also gives you the ability to choose between a lot more hardware. So it's interesting that that's the trade-off. We're almost there. From here, now that we have an operating system, most games are built on a gaming engine or development platform. That wasn't the case in the beginning of computer games, but now there are engines like Unity, Unreal, Cry3D, or Frostbite that have taken care of some of the common needs in a game. Movement, object interactions, audio implementation, lighting. You can use their standard commands or even checkboxes, and the engine creates the underlying code. Living in a 3D space is pretty straightforward, but actively creating one, or even a 2D space, is surprisingly challenging. As your perspective changes, what appears on your screen is a result of transformations, coordinates that shift from one frame of reference to another. It takes a ton of linear algebra or matrix mathematics to do this, and it's a huge amount of relatively small calculations that GPUs were specifically designed for. They can do enormous amounts of simple calculations very quickly, compared to CPUs that are more generalized and capable of doing both simple and extremely complex calculations. These game engines both simplify the math for the coder and also create code that is optimized for GPU utilization. The latest and greatest in gaming, ray tracing, takes this concept up a notch and makes it so that every light source in a scene is traced, giving amazing reflections and making games subtly yet amazingly more realistic. But that requires an enormous amount of math. Again, something that a combination of software and specific hardware is now tackling. And now we're at the game itself. With the code output from your game engine, you get a self-contained game that has the code to communicate with the operating system, which is built with a programming language that interfaces with the computer architecture of both a CPU and GPU, which is based on the discrete digital logic, which is made up of semiconductor CMOS structures built on a silicon wafer made out of sand. Each step is important. As the processor and GPU get faster, you can have more polygons in your games without lag, though you do reach a point where just more polygons don't really make that much of a difference. GoldenEye was awesome 20 years ago when I played it, but now it's just embarrassingly bad. And that's because every step of this process has improved. Things got smaller, faster, more efficient, better designed, all to create the best gaming experience. And that's it. We did a lot of simplification, hand-waving, and ignored just a lot of important parts of this, but at the same time, that is the general steps that you go from sand to our modern electronics. Now, if you want to learn more about the details on the electronics and electrical engineering side, we have a ton of tutorials on CircuitBread.com and on our YouTube channel. And if you're more interested in the materials science or the computer science aspects of it, then there's tons of stuff out there where you can learn and grow and pursue this. So hopefully this video has kind of inspired you and made you want to learn just a little bit more. And in the meantime, remember,
the next time you're walking on the beach, an hourglass, or making cheap, low-grade windshields. Think where we'd be without sand. Sand! Sand! Sand!
Okay.
Hope you enjoyed this video. If you did, give it a like, share it with your friends, and if you want to learn more about electronics and electrical engineering, subscribe to our channel. Take care, and we'll see you in the next one.